for the rectangle helps out tremendously. Okay, then so now we're going to integrate with respect to y. So if you look at this, that each of the rectangles we have now, picture yourself looking at this straight on the way you normally would, and now turn your head clockwise. So now you're seeing the top as the highest x value and the bottom of the rectangle as the lowest x value in the region that we're considering. So you see each of the rectangle strips has a thickness of delta y. So if I zoom in on this, it's delta y because the thickness, you can see it has a delta y along the y-axis, and I have that illustrated here in the second area from here all the way up to the area. So through the area, I mean. So here the same thing, delta y, and here we have the top portion would be over here and the bottom of the rectangle would be there, okay? So we have the f of y minus g of y. That gives us the height, and then of course we have the delta y would be the base or the width of each rectangle. However you would write that, the base, I guess we could write it for the delta y, okay? So this one's a little bit different. So we want to find the area of the region, the same region. So what we have to do, and when you read these, I know I've got all this information, is that we have our boundaries here. When we set up our rectangle, we have, let me get some highlighter going on here. I set up the rectangle, that's my first step, and I look, well, it has a delta y now, because if you look, the thickness of the rectangle is along the y-axis here, right? So delta y, and I have the top of the rectangle is along the red line, and the bottom is along the square root. Okay, so then I know that I only have one integral that I have to do, but it has to be in terms of y. So when we start this out, notice I have this expression. I think my pen, did I just lose my pen? I did. Okay, hold on. It's okay. Here we have our integral form. Okay, so what I'm going to do is I look at the top minus the bottom. The top is always f of y, the bottom is g of y, and I'm just designating it as such. So my f of y has to be, notice I take the function y is equal to x minus 2, and I solve it for x. X then is my f of y, because the red graph is on the top, okay? So notice that I have my y plus 2 here. Okay, there's my top. And then it's going to be minus the bottom function, which is blue, right? So I've got my y of y squared. Did I miss something here? Nope. Okay, so here is my y squared, g of y, okay? So that's the bottom function, g of y. But it's no longer y is equal to square root of x. I convert it to y squared is equal to x, and then x is equal to y squared. So x is my g of y. Function of y. So instead of having functions solved for y, y is equal to square root of x, now we have functions that are x is equal to a function of y. So now I'm going to leave this one up to you as well. Now remember that you have to get the same, something erased here, 2 squared over 2 plus 2. Okay, so I've kind of set it up here, and we'll leave the rest to you guys. You could easily integrate this, right? But you're going from 0 to 2, because we're using along the y values 0 to 2. We have the y values considered for the integration instead of the x values. Okay, so we should get the same integral. It should, I'm sorry, the same value for the integral. It's just 10/3, the same area, so it should be the same value. Okay, now the important thing there is when you're looking at the integrals, it is much, much easier sometimes to integrate with respect to y, because if you consider this last one, that I first got to decide which one is which and how this picture looks. So if I'm going to graph it by hand, or maybe I'm going to graph it in the calculator, but I have to know what this looks like. So in this case, if I was using the calculator, I would probably look and see what this thing looks like. Knowing that this equation, x is equal to y squared minus 2, it's both of these together. Y2 is equal to the square root of x plus 2. That's the top half of the parabola, being this half. And then you have y3 is equal to the negative of the square root of x plus 2, which is going to give the bottom half of that parabola. So it looks like this, right? So the thing is that the x equal equation allows you to put the whole thing together as one expression. Now, do you see when I put the orange rectangle in? It's much, much nicer when we're going with y's than going with x's, as I'll show you in a minute. So with this one, you're going to have to decide which function is on the top. And in this case, you have the x cubed function is on the top. Okay, this is going to be x cubed. So remember, it's y is equal to x cubed, but it's going to be x is equal to the cube root of y. Okay, so the top function is this one. Now the bottom function, you already have that. The bottom function is x is equal to y squared minus 2, right? And that's the bottom, left to right, everywhere. So the top is always the top, cube root of y. And the bottom is always the bottom, y squared minus 2. So we have the area that is equal to the integral from, I'm going to use c to d of f of y minus g of y dy. So then I have the area is equal to the integral. Now, notice I didn't put these points on it yet. I'm going to leave that go for just a minute and fill them in. So I have f of y as the top, so it's going to be the cube root of y minus the cube root of y minus the quantity y squared minus 2. Whenever you run into that minus between the two functions, you want to make sure you put parentheses before that second grouping. Okay, so you don't have a sign error there. Okay, now we need to find our value, our points of intersection with this graph, then, right? So what are the points of intersection for this graph? So you have where is x, y is equal to x cubed, and you have x is equal to y squared minus 2. So what you could do is substitution, where you have y is equal to y squared minus 2 cubed, and then we end up with y is equal to, what are we going to have? Y squared minus 2, I'm going to just multiply them through y squared minus 2, and then another y squared minus 2, right? So when I multiply the first through, I get y. Now remember, you have y is equal to x cubed. So we just plugged in y squared minus 2 in for x. So we only have y's now. So what do I have? Y squared, so we have y to the fourth minus 4y squareds plus 4. And then that's times y squared minus 2. Oh, this is really ugly. I think we should use a calculator for this. We're going to use a calculator really quickly. Yes, we are. So what do we get here? We're going to take y is equal to, I'm going to do the square root of x plus 2 in the calculator. Yeah, I've got to get on my way here. Plus 2, and then I'm going to take y is equal to the negative of y1, alpha trace 1, and then I'm going to take and put in x cubed, x caret 3. Okay, so I have my graphs in there. So I want to hit zoom. Zoom. So I'm going to hit zoom 6. And watching my functions come in, I just need to find my values quickly here. And though you could do this, now you have a 6-degree polynomial, and I'm like, so I'm going to hit second trace 5 for intersect. And what do I get here? Second trace 5, first function. Yep, second function. And it looks like I get 1.21, right? 1.2148648623. Boy, this is fun. 1.79 300 30037. Okay, So there is 1 point of intersection. Careful which value you use. And then we have another one down at second trace 5. And I'm going to leave that hit. There's the first curve is going to be the negative square root. So it's going to be in the bottom part. And then the second curve, I want it to be x cubed. And I don't want to guess. And it turns out to be -1, -1. Okay. -1, -1. One is so pretty, and the other one not so pretty. Okay, so when we put this in, what I'm going to have to do is go with the y values, right? So it's going to be, then you're going to have -1 down here for your lower y value. Keep in mind your dy integrals, so you need to use y values. So I'm going to go from -1. Let's take the highlighter off this, and let's highlight just the y value, 1.7937. Okay, so 1.79. What did I say? 1.7937. No, 30037. 300. And I'll tell you what, I'll store that, and I'm going to put that in for B. I think I'll put that in for B. So I'm going to STO. What I'm going to do is I'm going to hit the number. If I don't have it in my handy calculator, I'm going to type in 1 point. If it's in the graph and only in the graph, then I want to type it in 1.7930030037. Then I'm going to hit my store key, and then I'm going to hit alpha. I'm going to just hit the capital B. Enter. So then instead of that up above, then I can change that and I can just make that a B. Okay, so that's just my B value. So when you're on the AP exam, what you can do here, since we know that that's our upper limit, we're going to just call that, oops, here, thought I erased it. Oh, no, too much erase. For crying out loud. -1 to B. Okay, so what I can do, and then probably what we should do is call that B up there as well. Doop, 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 C to B. Who cares, right? All right, so there we go. So we would get an answer for that. I don't have an answer in my notes, so you can double check with me. I could probably get it pretty quickly, but double check, make sure. I'm sure the answer is reasonable. What we're interested in is setting up the integral. Now, say we wanted to set this up with x's. Note if we did, then we have two separate areas, one here and one over here. So the problem with that is if you look at what you have to find the points of intersection, which you do have. You know that this is at -1. This is at -1, -1, right? So with -1, -1, with -1, -1, you can go from the point here, which you also know. You know that's -2, right? So -2 is right here. So our function, y squared minus 2, so it has a vertex at -2. So you really could set this up as dx's. So look at this area. There's a rectangle here. Here's a rectangle. So we could do that, right? So I could go from -2 to -1. Now, this isn't too awful bad, but you have square roots in your integrand. The top function is the positive square root of x plus 2 minus, so here's the top. On that first section, this is area 1, if you will. Square root of x plus 2 minus, then it's going to be the bottom function there, which is negative square root of x plus 2, and that would be dx. Then you would add it to, let's change colors now. Let's make our rectangle green here. So then we would have the integral from -1 to, now remember, now the x values, we had that point at -1, -1. The x value is 1.2148. I'm going to cut it off at that. 1.2148623. Like there. And then the top function is going to be the square root of x plus 2. Okay. So you're going to go all the way. Here's that last point that we talked about that intersects with the cube root. The cube root of y, or x cubed. Y is equal to x cubed intersects y is equal to x squared, or square root of x plus 2 at this point. So we would go from -1 to 1.2148623. So we have the top function is the square root of x plus 2. The bottom function is going to be x cubed because now we're all in x's. And we have our integrand. Be careful with your rectangles here. I'm going to put this whole thing in a black rectangle. And there we have our integral set up. And we should get the same answer for both of these. Sometimes people don't like using two integrals, so we have one for the above. Other times they don't like working with integrals that are with respect to y, so they prefer to split it up like I have here. But again, you should get the same area for this. All right, so we have one more here, and this one just illustrates the idea that, and I'll let you handle this on your own, and we can talk about what you get for an answer for this. But keep in mind, with geometry, you can do some different things with this where you can do the integral of the square root of x, right? The integral of square root of x dx. And then you can go from 0, here's your rectangle, right? So delta x rectangle, we have the representative rectangle. The height of that rectangle is the square root of x, right? We could go from 0 to 4, and then we could take away the triangle area of 2. Okay, so that is kind of a nice little segue to end this lesson, but to notice that sometimes it's a lot easier to do something like this. But there are other times where you have to split up your areas. So you have